Okay, so not muted, recording. Great, great start. All right, hello everyone. Welcome back. Happy Friday. Hope everybody is here. A couple of things to discuss before I start the lecture. First, you should have all the class participation solution until number 10. I also added the solution for that double pendulum problem, and there's a video recording of that. So if you're able to follow that and can do that problem, you basically have it down, because that's one of the more complex kind of problem you'll see, from mechanical system to going all the way to state space. All right. I stopped at the state space, but you could convert. You could find the transfer function. You can find the poles. You can find PZ map for it. Like, you can go anywhere from there. The procedure is the same though. So I put it here. I try to put those in different locations. Since we are in week 5, you see all of them here. Next week, I will create a tab here that has lectures. It's going to be all the annotated lectures in one place. So when you're studying for the exam, you don't have to go back and forth. So you basically will have all of them at the top of your module. And then I graded CP9. CP10 will be graded, but you have the solution. You can go ahead and check. And then for today, we'll have CP11. So one thing that I want to talk about class participation is the deadline. All right. So, well, except for the 11:55, I don't know how that happened. It should be 11:59. So I'm sorry for that. CPs are supposed to be class participation. So number one priority, they are doing class time. Sometimes either the questions need a little bit more time, or the material I prepared for the day that I need to close it will take 55 minutes. So I leave the class participation open until 11:59. Now, the reason I don't leave it to next class time is I want you to check and evaluate your understanding of today's class, because you're fresh, you remember what we discussed. Usually those questions don't need much time. Is usually, do you remember what we talked about the state space? X dot is AX plus BU, for example. So the problem itself is very easy. You just have to do it once. It's proven if you do that, it will stay with you, the concept. So next time when you come, when you see it, you remember. So I'm trying to create that for you by adding the questions. So the idea is not to create a homework type of question, so you have something to do. That will be busy work, right? So that's the goal of class participation. If you have enough time, it will be due in class. If not, it's due at the midnight. Another reason is I have SLDS students in the classroom, so sometimes they get anxiety. So if the question is a little bit more time, I will make it due midnight, just that I can consider everyone. All right. So usually Monday and Wednesday are this type. Fridays, if the question is simple, it will be due in class. If it's not, it won't be due at midnight. I will make it due Monday before class, just because you'll have more time to study over the weekend if you want it. And it's Friday, everyone wants to just get out. All right. But you always have to check the deadlines, the due dates for the homeworks and for the class participation. The thing is, in real life, you don't have a pattern for things to be due. If you work in a company, there could be a meeting at 2 p.m. on Wednesday. You have to prepare something. Then there is another report you have to send on Friday this week. Next week, that report has to go on Thursday. So you don't have a pattern. You have to write it down somewhere. So if you don't have that system, create it. This is a very good classroom. This course is really good opportunity to do that. So I have 3 planners, one in my bag, one in my office, one at home. Make sure all 3 are the same. Everything is on my phone and everything is on my computer as well. So if I miss something like I should have missed, I messed up big to miss something. This is just how it works, right? So I know a lot of you do this. Sometimes missing something, I just simply forgot. It's okay, it happens. But if it was on you, then it's on you. It happens. And for CPs for this class, if you miss 1 or 2, it would not impact your final grade. But if it's more than that, then it will start having some impact, right? If you are an A student, if you just want to B, see something, so don't even worry about it. It will not impact you. All right, is that clear? I don't want to be mean or anything. It's just, I think this is the ethics that we need to learn as engineers when we go to workforce. And in all of my classes, I have that. This is actually the first class I'm adjusting it a lot and listening to my students. But this is like the end of what I can change. All right. So always pay attention. I always have them, the due date at the end of the lecture of that day. Also as a reminder that what you have to do after this class. It always says things to do after this class. All right. So pay attention to those as well. All right. You have homework too. Some of you are working on the homework, so that's very good. Okay, I'm gonna switch to my iPad, so I have to stop sharing this and share from iPad. We had one thing left from last week. I'm gonna finish that up, and then we're gonna work on MATLAB. And I'm going to just basically review that. So, quick reminder of what happened last week. Wednesday. We worked on how to transfer between models, especially from state space to transfer function. We found that the equation, this is the equation that you can use if you have A, B, C, and D. If you arrange them like this, you get the transfer function. Oh, sorry. And then solved an example. And we also said that we can find the poles from the transfer function. We can find the poles from our state space representation because they both are the same thing. What's the main difference between the two models? Brett, what's the difference between transfer function, representation, and state space? Yes, that's the main difference. The state space is in time domain. They both have to have the ability to show you poles, the stability of the system, what is the system, but they just have different ways of saying it, right? All right, that's why I can trust my TA and I can ask him question on the spot. That's what I expect. All right, right? So the poles of transfer function are the denominator. You put that sentence equal to 0, the polynomial. You find them. For state space representation, how do you find the poles? Now asking the classroom. Eigenvalues equal to 0, right? Well, if you find eigenvalues are actually the poles, if you want to calculate it, you could use this equal to 0, which is the eigenvalue. Okay. So if you find the eigenvalues. Now, so if you are following your book, so this is basically a bonus slide to help you to understand your book. I think this is a bit more advanced to be here. So I think your book, the way that they organize the information is not really good. These are more of 55, 51 kind of stuff. So if you are reading the book and you're confused what's happening, it's okay. So we use state space representation to design controllers. Sometimes it's easier if we had a specific way of representing, and then we could just easily transfer those to transfer function or manipulate them in our control system. One way is to put them in canonical form. So some system are, when we put them in canonical form, they're controllable. Sometimes we say they're observable, and that's all the way that we can arrange them. Now, the point here is that every system will only have one transfer function, but we can write different ways of, we have different ways of writing their state space representation. One simple fact you saw the other day, depending on how many change of variable you get, you'll have a different representation, right? And they both should be representing the same system. And they will, even though they will look different. If you write the transfer function, though, they have to be one, the same. Another way of writing and representing state space is to put it in a format that this row at the bottom here will have all the coefficient of your denominator in your transfer function. All right, that's one way of doing it. And then your C, which is your output, would be based on the coefficient of numerator and denominator. Why is this good? If our transfer function, if we can write what A and B's are, we can look at any transfer function without going through the trouble of converting. We can write one representation in canonical form that represent that transfer function. How we do that? We write, for example, this one here. So this is 1, 5, 3, 2. So this is A3, A2, A1, A0. Then I just simply put it here. I created matrix A without doing anything, right? But this is a very specific way of doing it. It does not apply to all systems, so you have to be careful. That's why this is more of advanced control, because you need to know more about your system to be able to represent it. But this is one way of representing that system without going through change of variable. All right. So finding A's. So the thing is, in the first column, you have 0, 0, 0's negative AN. Then you have 1, 0, 0, negative AN minus 1, all the way to 0, 0, 1, negative A1. So this is one way of representing a matrix from transfer function directly. Same, you just follow this equation, the relationship to find your B, C, and D. You see that I use subscript C. So this is controllable canonical form. It's a very specific form, and again, not every system will have these. So you can write it, but when you are trying to control, then you cannot control that system because it's not controllable. How do we know controllable? We don't know yet. We have to learn more. That's why I think it shouldn't be there. But this is just, if you see it in the book, that's just one way of showing the state space representation. Does that make sense? Or is it confusing? Make sense? So it will not show up in your exam at this point. It will not show up in your homeworks or in class participation. It's just for you to give a clue when you're reading the book, where did that come from? All right. If you have an example like such, all you have to do is what is N? This is N. And then I wrote what is my B0, B1, B2, B3. Same for here. And then I created a B, C, and D matrix following that equation. All right. Questions on this? So basically, if you want, you can just forget it. At this point, it's fine. We'll come back to it though later. All right. So I'm going to stop this one and then go log on MATLAB. You can do the same in your computers. So if you don't have computer or an iPad, sit next to someone that has. So you have time to move around. I'm going to give black screen for now until I find my lecture slide. You can also pull up the lecture that says MATLAB state space representation. Response rate. All right. All right, hopefully this will work for Zoom sharing. If not, I have to switch back and forth. All right. So things that we will do today, how to go, so using MATLAB, how to go from state space to transfer function and from transfer function to state space, super easy using the software. You already went through the suffering of doing it by hand. So this will be, I didn't know it's just that easy, or you might have known, I don't know. If you're doing a homework or exam, you have to do the manual way, but this is a good way to check things. All right, so if they were numerical, you can easily check. If they were not numerical, you had variables, then you have to use MATLAB variable. I don't know if you don't know it, then you have to do by hand. All right, MATLAB has a function that you could use variables and solve problems. Now, to create a state space object, you use a function called SS, so state space, and then the input of that function are four things: A, B, C, D matrices. So before this, you will introduce your matrices, and then you can create your system, which is that object, and you can say SS of those four matrices, and it will create this expression, this representation for you in MATLAB. Now, if you have a system that you build the transfer function, so you have numerator, denominator, right? You use TF, numerator, denominator, to create a transfer function object for you. That is from the last MATLAB class, right? So now we know the two commands that can create transfer function or state space. Their input is different. What they take is different, and then they both give us systems in our respected representation. Remember, transfer function is an S domain, it's an object in S domain. State space representation is an object in time domain. All right. Now, once we build those, let's do that. Let's create. Let's build this. Type this in your there. I mean, I know you have it, but I want you to see it. Your transfer function is this: 2s squared plus 8s plus 6 divided by this. Create this transfer function. Once you created the transfer function, we will convert it to state space. But for now, just create the transfer function. So call your system, whatever, system one. We're going to use it. Don't look at the solution, okay? We're trying to figure it out. Okay. So you can connect to your MATLAB online. Yeah. If you have an iPad, you can connect to MATLAB online. The good thing is, if you have this code later on for your assignment, then just copy paste it, right? So. Once you create it, so your step one is just to create this G of S. Call it whatever you want. Once you did that, you can use TF of that system to create a state space representation. So what does that mean? So this is my numerator 286, my denominator 18166, right? Based on this. If I want to put this in transfer function mode or representation, I say TF of numerator denominator. Now, that is a system, right? With transfer function object. If you tell MATLAB, now give me the SS of that, it would print this out for you. A, B, C, and D matrices for that. So you don't have to calculate it. You can convert between these two. So this is when you have the transfer function, you have the system is already in the transfer function form. You did it some part in your code, you already have the transfer function, so you use SS of that system. Okay, that's one way of doing it. Another way, let's say that we have the matrices A, B, C, D, right? We can say SS of A, B, C, D. Now, what if I wanted to get the transfer function of that steady space representation? We can use, are you done with this? Is everybody done with this? That you saw your ABCD matrices? All right. Now, if we have A, B, C, D, and we want to get our transfer function object, we can use SS to TF command, parentheses A, B, C, D matrix, then it gives us the objects for transfer function. So the first one would be a numerator, the second one would be your denominator. So you can create B and A matrices, right, vectors that hold the numerator and denominator. Then you can write TF of that. That should give you the transfer function. You can, instead of the first step that you created your transfer function directly, you could say, hey, I have my numerator, I have my denominator. Instead of saying TF, numerator, denominator, then SS, you can combine them. You can say TF to SS of B and A, which is the numerator and denominator. Make sure that you call them the proper matrices that you want. I should not be going away. Make sure that you call them the proper matrices. So on the left side, you have A, B, C, D. You can call them anything, but it's better to just follow A, B, C, D equal to TF to SS. So we went from transfer function to a steady space. You see that we have two ways of doing it. One is this way directly. The other way was how we did it here. To create the object first, then convert your object to the other one. Make sense? Both of these methods should give you the same. Which one you pick, depending on how you're writing your code, really doesn't matter. Are we good so far? So we just converted between the two representations, right? And we also know how to write each representation if we had their appropriate intakes. Now, do you remember we talked about LTI system and we said about if we have, for transfer function, for example, if we have an input, a signal, and our system is LTI, and we can, if we know how the response looks like, we can superposition different signals and we are able to guess what the response look like, right? Do you agree with me? That's what transfer function does, and that's why we use LTI system. We're using their specification. Now, one of the very useful signals we use as input to our system is a step function. All right, step function is just a function that is zero for all the time until you change the value. You can usually say zero for all the time. At zero, then you change the value, but really depend on whenever you want to change the value, it goes to the new value and it stays there. So it's just a step up, right? Sometimes a step down, but we usually work with the step up. So 0 and then can go to 1. If it is 1, is a unit step. But you can go from 0 to 10, it's 0, and at some point it changes all the way to 10. All right, that's still a step function, is not unity step anymore. It's just a step function with a value. So the next command is step command. You're basically using this command telling MATLAB, hey, this is my system, all right? Either transfer function or state space representation, doesn't matter. MATLAB can work with both of them. You'll say that, tell me what's the response of a step function applied to my system. Your system, let's say transfer function, then you introduce it and you give it time, a final time for how long you want this step to go, right? And then so you use a step for transfer function. I will give you another command for state space representation. So it will create y of t, which is your response, and a simulation time. If you miss this bracket y and t, you just write a step, sys and t and a time, it would still perform it for you. All right, but it doesn't log it somewhere specific. It just as an answer, just a generic answer. But the result of this is a plot. It will plot the response for you. So this is a step, our function ut. If it is unit step, is going to be 1. And then our output, which is our response, could vary depending on the system. You could have different outputs. All right. The goal is usually for the system to track that out, your step input. So if you want it to go to 1, it will show you how long or how it takes the system to follow and track and become 1. Usually our goal in control is to track it as closely as possible. All right, but for now, we just want to see how it looks like if we write the step. So for a system with a transfer function, okay, I'm going to show you the transfer function, but try to write it yourself. So this is the transfer function here. So numerator, denominator, create the transfer function, and this is your runtime for your step function. Plot the step, give the step function value, use the step function command and plot the response. You can label the axes. You can follow the lecture. So here you are giving a vector for time from 0 to 3, and your steps are 0.005 seconds, right? So basically, there are different ways of introducing this time vector. One way is this. There are different ways you could do that. And I think it's time span. So. Yeah, so I have it here. I'm gonna run. So you'll get something like this. While you're writing, I'm gonna make some changes and ask you to make that changes and tell me how it changed. So let's say this is. Did you all get this plot? Always change your axes. All right, so this is the wheel velocity. Now tell me, what's the state vector here? This is a transfer function, it's not even a state vector, but what am I measuring? What's the output? Velocity, right? So it wasn't there. MATLAB doesn't know. MATLAB just knows a bunch of numbers, right? This is the part you have to always add to tell us what they are. We're going to use the same commands you'll see, well, slightly different for state space representation. then if you have a state vector of like position and velocity, you have to identify which one is what. All right, so this is something that you always have to add to your code. A lot of us forget because just I apply the step function. What else do you want from me? Now, does this track that you need to step properly? What does it mean to track? Where do you see this? Like, how can we show that unit step? Where is the unit step? From 0 goes all the way to 1. It had to be a straight line, right? And you see that it's fluctuating around 1. It wants to go. So if you change the time to something else, like extend the duration of your simulation. What right now is 3, right? Make it 10. What happens? So basically the wheel goes fast and slow, fast and slow, fast in those directions until it gets to 1. It does what we want, but it's not following a very good behavior, right? What do you expect this to do? Even in 10 seconds, how do you prefer the system would behave to get to 1? I'm just checking if you have an intuition. What's that? No, just a shape. How do you expect this shape to look like? So your step function is from here, goes all the way to 1 and flat. So you want to follow that, right? In real life, you can't just change something to get to that speed, right? Because of inertia. That's why inertia is important. So what would be your preferred way, like, of response of that system? Let's say from 1, let's say the car going from 0 to 25 in the neighborhood, right? That's the same thing. How do you expect your car to behave? Do you want to be jerky motion, go like 50, 45, 35, 10, stop? Like me driving the first time I start driving, right? Everybody throws up in your car. No, what is your expectation? Smooth, right? So smooth is, do you see this curve? We want this actually to be here. Well, you want this to happen like that. Follow this. Go up and then flat out very quickly. You don't want it to be too quick. Again, it's going to be a jerky movement, right? That's what you expect. Right now, you're not getting what you expect. So this system is not controlled. It's just the behavior of the system. Eventually, we'll get to what you want, but you want to make sure that that happens really quick. So that's the control part of this course. Do you remember the kind of problem we have in control? You have 3 kind of problems. Do you remember the very first lecture? What kind of problem did we have? I'll give you extra 2 points if you can remember without looking at the lecture, Adrian. 2 points. Try to think and guess what kind of problem you can have. So you have the input and you have the output you want the system. Okay, that's one problem. System identification. That's one. Well, we keep 2 points, but you get 1 point.
We have the input in the system and one output.
That's the second part, right? What's the third part, Michael? Why? Because you have a desirable output. You want to know what kind of input is that output, right? So Drew, James, and Michael. Congratulations. 3 points. Right? Can you take those points out? Oh, last name Drew. What's your last name?
Shepard.
Okay, we have 2 Drews here. All right. So when you wrote the transfer function, you had the output, you had the input, you created the system, right? You did the system identification. Now, what problem I just solved? What problem I tried to look at? I had the input, I had my transfer function, I looked at the output, right? Then I say, the output doesn't look good. Then I have to go and manipulate my system because I have a desired output. You just said smoothly go to that part. So you know what kind of desired output you have. Now you want to find the proper input. Or you might say that I have to control my system. So you have to go back to the system identification. Add the controller, find transfer function, do this again. So every time you will do one of these three tasks, you just don't realize what you're doing. Because the question was not which problem you're solving. I asked you solve this problem. But every time you find the transfer function, you did system identification. All right, this is the first time you had the input, you had the system, and you looked at the output. So simulation, that's simulation problem, right? The goal is to do the control, to find the improper input. All right, so the next step, let's say if we had the state space representation, how do we show this? So instead of using a step directly, we can use LSIM. So LSIM is not one sim. Use LSIM command, you still give your system, but you tell them what your output look like, your input look like, your U. Then you can give your time for the computation for simulation, and what's your initial condition, optional. You can start from 0, but sometimes you have a specific initial condition. Your car is at 5 meters, or you have initial velocity. So you are going 25, you want to reach 250. How should you press the pedal, for example, right? So, but this is option. If you don't give it, it will assume it's 0. So, but the still system is LTI. We can use step, for example, to see how our system behaves. Now, this is an example. I want you to type this out as well, so you have it. Your system has 4 matrices, A, B, C, D. So we know this is in a state space representation, right? Then create the system. Here you have initial condition. You have a time vector. So your time is from 0 to 1. And then your input, we are creating a 0 input. Just to show you, 0 is also an input, right? So if you want to be 1, you say 1 times the time. So you can create any kind of input here you want. If I don't have an input as a force, what is manipulating my system? Solve this, then look at the solution, then see if you can find what changed the system. Because there is a motion happening. I want to see if you can understand what caused that motion. By looking at your A matrix, can you tell me how many state vector you have? You have 2, right? Because A is 2 by 2, so you expect to multiply by 2 by 1. There must be state vectors with 2 elements. So when we say we have 2 state vector, like 2 elements in the state vector, we need 2 plots because we are tracking 2 things, right? That's why you have subplot. So if you ask, how do I know I have subplot 1 and 2? Because you are tracking 2 things. Plot this and raise your hand when you're done. Oh, it doesn't matter. Yeah. So when you, okay, be careful if you are writing those back to back. Know that you're overwriting your previous variables, right? So I usually create separate scripts for them. So if you pull up my computer, my MATLAB, my first chance state space, my first chance function. So name and create from beginning, because let's say I use T in part of my code and I forgot to create a new empty like time vector, for example, and I just used it. It's going to use what I had previously. So I would like to do different. What should we say? Elson. What's that? You can run by section, make sure that it's allocated to value. You're using the let's say that this is fine, but let's say you have this is good. Okay, who has the plot? Plots. Tried it. Because then if it's on MATLAB moment, I'm gonna have to write it.
Oh.
All right, everyone. Did anybody read what? This is like you just basically are typing. I'm going to show you how it looks like because I want you to think about the question I asked. We expected two plots, right? One is x1, one is x2 because we named it, right? We expected two element in our state space vector in our state vector. So the input was 0, right? We said 0 times t, so basically 0. But we see a motion in our system. What does that mean? What could be the cause of that? Is it inertia? Okay. Relates to inertia somehow. You can't connect it to inertia. But what caused it? Look at the code. What do you have in there that could cause a motion? You don't know what our system is like. You don't know how it looks like. I didn't tell you what system it is. Elizabeth? What's that? Yeah, the question was, you'll see a motion in the response, right? The thing moves. X's position is moving. The input is 0. U is 0 times t. So what caused this change of position? Going from something to 0. So you should be able to read this plot. X1 is going from 1 to somewhere. So if you extend this duration of simulation, it will go towards 0 or some point and stop. Right? We see that the position starts from somewhere and then like lower. You don't have any input in the system. What caused that? The initial condition. Think about what system can you bring as an example that will cause that? Anything that restores energy, if you give initial condition and you let it go, so you don't have any input, just let it go, right? It can go back, or think of the pendulum. I pull, I'm starting from here. All I do is just let it go. I'm not applying any force. The inertia, the force of gravity, whatever is in the system, the restoring causes this. So sometimes just the initial condition of the system will cause that motion, right? So a lot of times we can calculate that as phi, which is, we call it the state transition matrix. And it just shows that how the initial condition of an unforced system can move that system or can cause the motion. Now, you will see the theory of this next week in class. So just so you know, using MATLAB, you can use this expression and calculate it. I will explain the mathematics of it next week, all right? But if you have initial condition in some systems, it will cause a motion. Some system, it won't. For example, this pen was here, I moved it here. I'm not applying force. Is it moving? No, because of the system is not moving. But there could have been a system like that, and then it will move, right? So this phi kind of explains the A matrix. That hey, the A matrix, it has some relation with A matrix. We will cover this in next week's class. You have 5 minutes. You already have a code for the last example. This is a practice example. You don't have to submit or finish. But I want you to try to solve this. Your class participation is something like this. This is an example. You have to plot the step function for that step response. So here, plot the step response to the mass spring system. You see your system. You should know how the equations look like. You have it probably in the lecture. And those are the model parameters. Start coding. And you want to know the response of the step function to the system. So this is the time of simulation. You didn't do something that you have on the screen. But it doesn't have a. Right? So that time is simulation. So how many, at what point of time do you want me to solve this problem? And it's what? Yes. Yeah, this is our group. So control triangle. If your personal MATLAB software doesn't work, you need to install Control Toolbox to be able to access your TF, SS, TF, to SS, SS, TF, and everything the same. Control Toolbox. But in class, it's good to use your MATLAB online because it has a basic. Okay, so you can different names. So this is. Remember the different so someone else asked this question. So when you use SS to TF, was that TF to SS? And if you use separately A, B, C, D equal to SS, like SS of something, you might get two different A, B, C, D matrices. Remember that a system can have different state representation. You have to check, like if you check matrix A, don't check one row, check all the elements. They are different. One of them is in canonical format, control canonical format. The other one is not. You can have multiple way of representing in a state space. They're all correct, but they all come together. But if you run those two and check the matrices, you see they're different. But it's okay. It can be because every system has only one transfer function, but many different way of the state space representation. One could be canonical form, could be observable canonical form. There's different ways. Yeah. So what is happening? Let me, I'll get back to you before I finish the class. All right, so this is just for a practice. I post the solution, all right? But you have a class participation. I'm gonna show it here and then you can leave. Just wanna make sure that everyone knows what's going on. That has more points, so you don't wanna miss it. That's next week. Design, it's a design problem, all right? So your class participation, which is due Monday, you have a block diagram. I've explained what it is. This is a satellite single axis attitude control system. So it has this controller in there. So someone designed it. You're gonna show the step response to a 10-degree step input. It's not 1 anymore. The only difference is you have to adjust it to 10. My suggestion is do with 1, just a step, and then go try to do 10. To do that, you might need to do some reading. How do I introduce a step of more than 1? All right. That's why you have 2-3 days for this. Then I'm also asking to change the values and see if it makes any difference in your response. So kind of, you need to write maybe one paragraph of report. What did you observe? It's not a report, just what did you observe between these different cases, all right? So read that properly. And then when I say PZ map, if you just write PZ map and transfer function, it will plot the polar geometry. All right, that was missing in one of the class participation. Now, I will get back to you. I'm going to close this. So class is